will be presenting our guest, Jean Bresson. Jean has did his PhD, I think, at UNICAMP a while ago. Has been working there on the development of open music, and we'll be talking about this software. Has been developing composition initially, has been also applied to a variety of other fields like music analysis. Today we will be presenting some aspects of this very powerful software that is open music. So please welcome Jean Bresson, who will be our guest this morning. Thank you.
Okay, works? Yes, good. So, hello everybody, bon dia. I changed a little bit the program as compared to the topics announced initially in my abstract, because I plan to show some recent projects around computer-aided composition, and one of these projects concerned this an opera of Palestra that took place 2 years ago, which involved sound synthesis in particular, sound synthesis processes, and then I thought it could be interesting at the conference to focus on this particular work and try to go around and see some different aspects of computer-aided compositions using this example as a main thread of my presentation. So it's a little bit different, but the same topics will be addressed between today and the talk of tomorrow. So now it's titled Composing with Sounds, Composing Sounds. So I will try to relate everything to the idea of using sound analysis in composition and using computer-aided composition to deal with sound analysis and sound synthesis. Yesterday, Gerard presented a little bit the general ideas of computer-aided composition and the open music environments. And as he said, it was initially designed to work in what we usually call the symbolic part of music, of musical structures, like typically scores and all the thing you deal when you are composing music. But some recent works have been carried out by myself and before that by other colleagues in the music representation team to try to extend this idea of composing with computer, not only to the field of symbolic music and scores, but also to the field of digital sound processing and sound synthesis, sound transformation, sound analysis, etc. So this working in these aspects involves a number of differences and paradigmatic shift as compared to traditional music composition with computer. In particular, we have to deal with micro and macro levels of the musical and sound representation. We have to deal with some psychoacoustic issues. We are not dealing exactly with the same kind of musical information, and that's also not exactly the same aesthetic targets that we are addressing in this work. So we are going to be focused on the open music environment, so I won't spend too many time presenting it. Some of you already know it, and Gerard explained a little bit yesterday. So that's the idea is that we are in a visual programming environment that composers use to generate, transform, modify, do any kind of algorithmic or programming activity using graphical programming and some specific data containers that are usually related to scores or other kind of musical representations. In our case, we will deal a lot with sounds, control curves, and relate this to the traditional musical representation. I will speak of I will give some examples, as I said, in Marcos Ropa's recent opera, but I will give some other examples that are extracted from the OM Composer's book. It's a book that we published a few years ago. There are 2 volumes actually, and it contains some experience. Every chapter is written by a composer, and it describes his use or use of the environment for different these compositional activities. So I will show briefly some examples taken from here and take more time to focus on Stropa's work. So just a quick introduction on Marco Stropa's opera Rehearsal. It was premiered in 2012 at the Opéra Comique in Paris. It's an opera for 4 singers, 4 actors, 11 instruments, and voice and invisible sounds. So, as stated in the presentation of the work, the synthetic voice and invisible sound are all the electronic parts, and they are considered the same as the other performers and actors in the general sketch of the opera. So that means the composer tried to give the electronic parts the role of a character in his story and in the work. So the initial libretto is extracted from an old story from Arrigo Boito, and it's been adapted by Catherine Alioni, Nicola, and Giordano Ferrari. So the first aspect of this opera that I wanted to emphasize here concerns the use of sound analysis models, which means trying to extract some data from sounds and use them in the compositional processes. In composition in general, there are lots of different representations that can be used as compositional data, but we usually tend to use the spectral representation. Composers usually do. So this is a spectrogram of a sound. I guess most of you are more or less familiar with this representation. It's a time versus frequency representation, and the grayscale represents the amplitudes. This view is built by a sequence of Fourier transform frames that make this global timed representation. But in the musical application, we used to consider these partials that I represent here with the red lines, which abstract the main sinusoidal components from the sound spectrum into some more close to symbolic structures. So the use of this kind of representation is quite commonplace today. It was introduced and developed quite a lot by all the spectral composers, Gérard Grisé, Tristan Muraille, Claudie Malherbe, and others. In the OM Composers book, there is a text from Claudie Malherbe that is interesting, and that's where I extracted these pictures, which describe the different paths he devised between the sound representation and the score representation and all the symbolic manipulation that can take place between all of these representations. So some processes that are described and that are still, there are not that much basic processes that are used, is the idea of segmenting the spectrum into relevant entities, trying to detect the partials, as I showed before with the red lines on the spectrum, and somehow making some averaging of the partials into the different sound segments, which allow to go from a low-level representation, upper and upper, to something that resembles a kind of score. It's a time versus pitch representation and to conversions to score like this. So all these different scales of representation are as much levels at which a composer can work to transform and use the compositional data. So this process, as I said, have been used and developed quite a lot by composers. In particular, the different tools developed at UNICAMP are very much oriented to this kind of manipulation and transformation in the audioscript software, you can do analysis and export the result of this additive representation of the result of partial tracking. There are different file formats that you can import in OpenMusic and make some different kind of transformation to convert this result of analysis into symbolic score representation. More recently, we have worked in some specific tools. You can see here, for instance, the transient detection or the chord sequence analysis boxes in OpenMusic visual programs that allow you to communicate directly with the sound processing engines that are initially containing software like AudioScript. And within your visual program, within the compositional process, perform the sound analysis processes in order to complete the cycle from sounds to symbolic representation without leaving the environment. So these are a few examples taken from the Web Composers book that use these kind of processes. The piece from Grégoire Lorieux, Langage de langue, uses some sound analysis to create some kind of library of different musical structures that he used after in his composition. There is another interesting example by Permanus Lindborg, who analyzes the sound here. It's the spectrogram of a sound. It's actually a discourse from Mao in China. And we see some kind of gray areas which correspond to the moments where the audience is applauding or shouting or something. So he makes some analysis of this structure and extracts some pitch and temporal patterns that are supposed to mirror the emotional contents of the overall discourse. So that's just to give you some examples of the various and different things you can do with this kind of project. So in the rehearsal opera, this process is used at different moments to generate different parts of the music. One is to control the disclavier. So the disclavier is an automatic piano. You can control it with MIDI. It's called DSKI. That's the disclavier from UNICAMP. It's a joke with Dominique Strauss-Kahn, the politician, because it was at the same time. And so Stropa divides some processes that allow to make this instrument somehow alive, because he wanted to have every character in the opera associated with an instrument that represents his mood somehow. So there is one character, this one is associated with the disclavier, and the disclavier follows him on the stage and reacts a little bit like, depending on what he says or what he does. So I will just show you a quick example here. We'll see two videos. This is the shooting from the opera, and this is a studio recording session focused on the piano keyboard. So I have tried to synchronize the two, but they are not exactly synchronized. Hear the sound? So I make the sound is this one. keyboard reflecting some. So I will show you the Open Music patch corresponding to another section. Maybe we watch the video first. So that's another part where this character, I don't remember his name, but is laughing, and so the piano will try to be happy and laugh too. So the Open Music patch responsible for this part of the display is here. You can see it's not that big, but it generates a very complex score. So at the beginning of this process, we start from this. This is an SD file. It's the result typically that is exported with AudioSculpt software after sound analysis, which extracted the bashas in the sound. So all the bashas are in these SD files, the frequency and amplitude information. They are stored into some containers. So I'm evaluating everything in real time, so this process is a little bit long because there are lots of data. You will see I will open. So in this box is, so we have a few comments from Stropa here. It says this is the raw model of the sound. This is because there are too many time markers in the sound. So that's all the data that's been extracted from every single little gray dot here is a time frequency information. So the first thing the composer does here is to process this sound model with some rounding and filtering rules. So this is all programmed here. I will not get into too much detail, but the result is that the different pitches are rounded to the closest pitch from the keyboard, so just semitones. While here we had the whole frequency precision. So now we either remove or round to the closest pitch, and some of irrelevant information, for instance, if amplitudes are too low or other rules that are just defined here, are taken into account to lower the amount of data. So we see there is a bandpass filter, an approximation of the frequency, and at each moment it keeps only the, I think 100, the four main partials. So at every single moment you have only, if you make some vertical lines, you will find only 4 at the same time. So this information is still in the kind of spectral area of representation, but it can be converted directly into a score representation. That's what we have here. That's the first version of the score candidate. That's not exactly what the piano plays on stage. There is another step of processing here. What this step does is also a kind of simplification, but also of randomization. Because if we look here, we see that, for instance, the same frequency tend to append a lot, except especially in the higher frequency areas. So he wanted to randomize these lines at the top in order to make the score a little bit less regular. So that's what we have here. Okay, and then there is a kind of quantization process that makes all this into a rhythmic representation, because even if it was supposed to be played by the MIDI piano, we wanted to have the score, and the score is stored with the score for the other instruments. So that's what we get if we evaluate these ones. So that's the one representation of the score for the display. Now we can see what's the final result on this video. That's more or less what we just heard in the opera. But I would like to let you guess what was the original sound, if you didn't hear it. So that's the transcription of this passage from La Donna Immobile, sung by the Disclavier. The original sound being recognizable, but it takes something from it and retranscribe it into the score. Now you know it, I'm sure it's much obvious if you hear it again. Just for the fun, and I switched to something else. It's not related to this analysis models, but at the end, the character dies and is killed by another one. So you will see how the composer made this clavier die too. So he made a kind of gesture on the score, which gives supposed to give this impression. Then it lasts a little bit more. So here is a generation of the score plus the MIDI controllers that are responsible for the pedal of the piano. So you know already some part of the story, that the guy dies. I'm sorry. And I will have to tell you a little bit more about the story after. The second stage after this analysis and extraction of models from sound analysis is the bridge to sound synthesis. Because when we have some representation like this, it's quite easy to put them back into a sound synthesis process where each of these partials here, the time frequency curve, are used to control an oscillator and make some additive synthesis that will produce some sense of the contents of the original sound. It can be additive synthesis, but it also can be any kind of process that someone understands what's a frequency and what's an amplitude. So it's almost any kind of synthesis processes. So it's also quite a common use of this representation in open music to use them for feeding sound synthesis processes. I have this old example from Stropa that example what you can do in this kind of approach of the sound structure. It's in this piece from 97 Come Naturali Foglia, and he used the sound at the beginning. So this time I let you hear the sound right now. It's a fisherman's song from a Rhine. So these are sonogram analysis of this sound. So you see, it's kind of close to the representation we have now in the open music objects that I showed before. So the sound is analyzed, is segmented into pieces, and in each segment there is an estimation of what are the main frequencies in this segment. That makes a kind of a skeleton of the sound, and this information that correspond to our time versus frequency model of the sound are used to parameterize some different kind of sound synthesis processes. So this is with oscillators. This is the same data with some noise synthesis. So it's a noise and some filtering. Okay, you can use the data not to parameter oscillator, but to parameterize bandpass filters, for instance. This is why with a frequency modulation synthesizer. So then, in the same idea as before, with taking the model of the sound and transforming it in order to make the sound less recognizable and keeping the skeleton, the internal structure of the sound, Stropa made a lot of different experiments that take this structure and transform into some different sounds. So fortunately documented a little bit, so we have some information and some sound extracts. For instance here, he says pan from right to left, 10 to 20 subcomponents. So what he calls subcomponent is when you have one time frequency component, it creates a lot of smaller components around this area of time and frequency in order to generate some kind of cluster feeling in the sound. So it says each partial has 10 to 20 subcomponents, sounds more clustery. The spectral amplitude and duration of each partial progressively reversed, which produce a finite chord with the higher frequencies being the longest and loudest. Another example, slower tempo, pitch transposition, more clustery, more independent individual partials. Here, very large, I read because it's small. Very large clusters, 20 to 100 subcomponents around each partial. And this one, exponential accelerando and percussive attack, bell-like. So in this example, for instance, you see you can keep the same frequency component and take the time of the different segments and make some processing just on this time information. Before, for instance, scale the first one to be larger and then accelerate, and you get a new structure that can produce this sound. So let's hear a small extract of the piece of the recording. It's a concert recording, so it's a vocal ensemble and the electronic sound. So if you listen, you will hear most of these sounds I've played independently. They are all composed into the global electronic accompaniment for voices. the end, we just heard this one with the accelerometer. So I've shown it in the previous example with the discladiate, but we have these objects that allow us to represent this intermediate data between symbolic and spectrum using visual programs. So back in the real opera, we can also find some examples of this kind of process. In particular, there are different examples of Bell sound synthesis. So that's also kind of a similar process. We start from this sound. That's the Westminster Bell in London. An analysis of this sound gives us this kind of simplified representation. So we have different segments that have been, I don't remember, either extracted automatically in AudioSculpt, or it can be set by the composer prior to analysis. So we have this time versus frequency information. And then different kind of processing transform this representation into, for instance, something like this. So this is a set of spectra that overlap each other, because the time segmentation has been modified here in the intervals. It's a visual program that generates the interval. And the frequency content is taken from here, exactly the 6 first, the contents of the 6 first regions in this one. Then there is a process that transforms this representation into the control data for a sound synthesis process. So this conversion is controlled in this visual program here. So I'm not getting into too much detail either, but the idea is to scale the frequencies between the lowest frequency of each segment and the maximum frequency of the overall sound. So that makes quite a transformation in the frequency content. The durations are also transformed here with this BPF that is entered as a parameter, and this is an amplitude profile for the different partials of the sound. So all this is used to control additive synthesis process. Every single data will become an oscillator controlled in the frequency, duration, amplitude, envelope, etc. And we generate new kind of bell sounds that are not exactly the same as the original one, but take some of its structure and are used and take some of the compositional input from all this process. So in here, I just took the 6 first segments in here, in this structure, in order to accelerate the process, and we will generate a sound made of 6 So the synthesis for the technical information is performed by C-Sound. So what Open Music does is it just writes C-Sound files for the score and the orchestra, and then it makes a call to the C-Sound program that is installed separately on your system, like we do for Super VP or PM2 with the analysis processes I've shown before. So that's our result sound. Okay, so I've been through these different segments that have been defined here. For each one, a different scaling of the frequency content, and this amplitude envelope that gives a new kind of bell profile for the sound. In this patch, it's quite a similar example, but I have added this of it's part of Stropa's experimentation, but he never kept this for the final version, where also slight delays are applied to each individual component in the different segments. So that will make quite a different result. And the delays are growing over and over. Okay, so that shows that you can use the same initial structure and go to a very wide universe of possibilities depending on the different transformation and the choice you make in between this analysis and the synthesis process. So back in the opera, we can see the actual extract where we hear this sound. So I simplified a little bit the patch here because it's much longer, and even on the video here I have cut and pasted in order to make it a little bit shorter. So that's different parts where these bell sounds appear. You see at the beginning they are quite different, a little bit like I did before, and at the end they look very much like the original sound. So you may have picked another information at the same time. All other characters are also dead at this moment. So now this one is the last one. It's well, I'll tell you more about the story after. This the previous part from the combinatura di foglia piece from Stropa also showed an interesting aspect, is the link between the sound analysis and resynthesis with the score. If you hear what the singers were singing, it's quite close to the synthetic sound we use. So that's another thing that Stropa takes much care about in his work. Traitoria is one of his first electronic pieces from '92, and he didn't use open music at that time, but he already had this kind of concern that are quite obvious in this piece, and in particular I would like to, should have made it before, but here the extract where, so the piece starts with piano solo and progressively switch to electronic piece. And the moment where the switch from the piano and the electronic is quite subtle, and you see that the electronics is generated from the piano, and the piano part also takes care of being a sweet transition to the electronics. same tools, another composer. That's back also again in the OM Composer's book. It's a piece by a former cursus student at UNICAMP, Tolga Tuzu, which also emphasizes this relation between the sound analysis to synthesis approach and the relation to the score. So the process begins with a sketch drawn by the composer that is played by a bass player who actually plays two basses at the same time. This is the analysis of the resulting sound. Then the analysis data is used and processed in OpenMusic to generate some symbolic score parts that are used, and also some rhythmic cells using different processes of the analysis data. And this data is at the same time used to regenerate the score for the player and the synthetic parts of the tape. And then the piece is played by the bass player again and the electronics. So, short extracts. We have this of the The other part in this work with Tropa that engaged lots of research and developments was the synthesis of voice sounds, which have been done using the chant synthesizer. So I will make maybe a technical introduction of this synthesis technique and then show you also some examples of the compositional process. So the chant synthesizer uses the FOF, fonction d'onde-formantique or formant wave function technique. It's been developed by Xavier Audet and his team back in the 80s at UNICAMP. So it was quite an interesting technique because it allowed to generate powerful and realistic voice sound with very low cost of computation. The idea is to use these formant wave functions. They look like this. It's kind of a sinusoid plus specific shaped envelope. When you generate trains of impulses of this little sound, like kind of synchronous granular synthesis, you obtain this kind of shape in the sound spectrum. Which correspond to, in the vocal sound analysis, formant. Formant is if you look at the voice sound, you will see some kind of big shape like this, which characterizes the voices of the speaker, and the vowel is same, like A, O, U. So this is determined by this general shape. And so they discovered that by precisely tuning the parameter of this simple waveform here, in particular the slope and the different parameters that determine the shape, you can also determine the shape of the formant over there. So you can determine his central frequency, his bandwidth, his amplitude, etc. So the idea of the FOF synthesizer is to use several of such generators in parallel with the same fundamental frequency, the impulse of the trains. So the fundamental frequency makes and the different FOF that you would have in parallel would generate the different formants that characterize the voice sounds. So in here, this simple process with one formant, one single train of impulse would give a sound like this one. So that's supposed to be kind of a O. And if you put 5 such generators in parallel with different parameters so that you get these 5 bumps in the spectrum, you get a richer sound that gets closer to the voice sound. Still sounds a little bit electronic, but then the fine-tuning of the parameters fix it. Then all the process of using this synthesizer is to precisely, as I said, tuning this frequency, amplitude, bandwidth, shape of the grains in order to make some realistic or non-realistic voice sounds. So an interest in the Chant synthesizer in particular is that it allows you to set this value of parameters at different points in time, and then it generates interpolation between the values automatically. So for instance, I have made some quick sounds. Okay, in this example, I just gave 2 values for the fundamental frequency, one at the beginning, one at the end, and the synthesizer makes it. So this is also practical when we will try to make some voice effects like tremolo, vibrato, or transition, like singing, because you don't have to shape everything, but the synthesizer does a lot of the work for you. A more strange example. Okay, you can do any kind of variation of the parameters, and the synthesizer makes it for you. So this is a little bit of history on this project. Maybe I don't detail too much, but there have been different environments before that have been used to control the synthesizer, but since the 90s, the last one was default environment. It allowed to combine phonemes to regenerate kind of concatenative synthesis method, and since then there has been no more work on the synthesizer. So what we did is just to take the synthesis kernel of this environment and try to control it from open music. Okay, other implementations have been done meanwhile in Max or in C sound, but they don't provide these automatic interpolation features that the original Chant kernel had. So in open music, our problem is quite simple. It's just to set these parameter values for different points in time. So we have a virtual timeline like this, a different kind of batch of synthesis that gives us a number of parameters, and we set the parameters of the value of these parameters at several points in time, and then provide this to the synthesizer. In the 80s, the analysis synthesis team wrote a manual for Chant, which has been very useful in this work because it contained a lot of information on how to generate realistic voice sounds. For instance, there is a database of values for the different formats that correspond to the A, E, O, E for different kinds of singers, alto, soprano, etc. It gives some rules like this that ensure that the sound is also correspond to real voices. For instance, this is a relation between the frequency and the bandwidth of the format. You see if you make some analysis that this follows this kind of shape. The higher the frequency and the higher the bandwidth of the format. Well, this one is also very useful. It's a relation between the fundamental frequency and the frequency of the format. For instance, if you have a sound like O, you have the first format at a given position in the spectrum, and if you do O, the format also shifts with the fundamental frequency. It doesn't shift exactly the same, and it depends on the different vowels, etc. So we have this information that was useful also to generate some control rules for the synthesizer. So with all this information and some control data that can be extracted from any, generated from any process, we generate a file. It happens to be at the SD format, the same format that was used for the sound analysis and audio script. And this SD file is provided to Champ for parameterizing the synthesis. So that's the technical aspect. It's not very interesting, but you see that that's the scheme of an example file. That it's not like an audio file where you have to sample all the control data. You can just choose to put some control information at different points in time, and the synthesizer will make all the continuous variation for you. I will switch to more interactive examples here. For instance, this one. This one is a OM Champ synthesis patch. So what it does is this function gives me one of these values, A, E, O, U, randomly. And this is alto, bass, contre-tenor, soprano, tenor. So every time I evaluate this, I get a different combination of singer and vowel. And then I will use this to produce some information for the fourth control data that look like this. It's kind of an array of parameters. And this is a curve for the fundamental frequency of the overall process. So you generate these two main information, fundamental frequency values for the fourth generators, and then you connect this to the synthesized box here. I will initialize, so you see it's real. And make this one. Okay, so in this case, every time I evaluate, I will get the same frequency, but different powers. This example is quite similar. I don't choose anything in random, but I choose an alto O. And first I will remove this and the fundamental frequency curve. Okay, you see it follows. I can change. If I say alto E. And if I make some change in here, I will change the fundamental frequency, for instance,